Bismillahirrahmanirrahim. Today's our topic is valence shell electron pair repulsion theory. We know that Lewis octet rule is unable to determine shapes of molecules. Lewis octet rule gives us an idea about how the atoms in a molecule they obtain octet. They will obtain octet by either sharing of electrons or by losing or gaining electrons. In this way, the electronic arrangement around the central atom plus the electrons which are linked to the central atom, their electronic arrangement is provided by Lewis octet rule. However, we have to determine the shapes of molecules. For determining shapes of molecules, the first important theory put forward were valence shell electron pair repulsion theory. These theory were put forward by Sedgwick and Powell in 1940. After that, these were refined. There were some increments introduced into this theory, and these refinements were made by Nolan and Gillespie in 1957. First of all, I will take the ideas of this theory. First idea, the central idea of this theory is, we know around the central atom in a molecule there are electron pairs. Those electron pairs, they are the bond pairs plus lone pairs maybe. These electron pairs, they carry negative charge. They orient themselves around the central atom in space in such a way such that there is minimum repulsion in between them. That means there is maximum distance in between them. That can be also meant as they are maximum away from each other. This is the central point of this theory. Again, I will repeat. According to this theory, an atom, central atom of the molecule, is considered as a sphere. On that sphere, there is an arrangement of electrons. Those electrons, they will remain on the sphere in such a way such that there is minimum repulsion in between them. That indicates there is maximum distance among the electrons which are around the central atom. Second point of this theory is, we consider a multiple bond. That means a double bond or a triple bond, simply a super pair of electrons. So double bond is not considered as two bonds orienting in two different directions. This is simply a single super bond pair. Similarly, this one, triple bond, is also considered as a super pair. Third point of this theory, which was introduced by Nolan Gillespie, this was about the repulsion of electron pairs, how they repel with each other and to what extent. For example, I will take this. There may be bond pairs around the central atom. Bond pair repulsions are considered as least in comparison to bond pair lone pair repulsion. They are lower than lone pair repulsions. Now, why this type of arrangement, this type of sequence occurs? Because we know lone pair is a pair of electrons that is around the central atom. That means that belongs to the central atom wholly and solely. However, bond pair is a pair which is distributed between two atoms. One the central atom, another one as the atom which is linked to the central atom. So this is shared between two. Bond pair is shared between two, so it will occupy a less space in comparison to a lone pair around the central atom. That is why these bond pairs, they are considered to be having among themselves less repulsion in comparison to if we have two lone pairs around the central atom. They will repel each other to a greater extent. Why? Because they wholly and solely belong to this central atom. They are the property of this central atom. They remain attached to the central atom. They are closer to the central atom. That is why they occupy more space around the central atom, and due to that reason there is more repulsion among lone pairs in comparison to two bond pairs. These are the main ideas of this theory. We can now apply these main ideas to discuss the shapes of molecules. First of all, I will categorize the shapes into two types. First type is only those molecules containing bond pairs only. Those molecules containing bond pairs only around the central atom, we will first of all take the shapes of those molecules. After that, we will move to those molecules around the central atom there are bond pairs plus lone pairs. So first of all, moving towards this side, I will take examples just like this. For example, carbon dioxide molecule. The Lewis structure of carbon dioxide molecule is like this. Carbon having 4 valence electrons, oxygen having 6 valence electrons. So this will share 2 electrons with this. After that, there will remain these 4 electrons on oxygen atom. Similarly, on this oxygen atom, there are 2 lone pairs. Shape is determined only by the electrons which are around the central atom. So not by the atoms which are surrounding the central atom. So there are around carbon atom, there are 2 pairs. 2 pairs means 2 double bonds, one this side and another one this side. This pair is a super pair, so oriented in a single direction. This pair regarded as a super pair oriented in a single direction. So no lone pairs around this carbon, only bond pairs. These 2 bond pairs, these 2 super pairs, they will remain away from each other as far as possible. As we know already, in case of 2 pairs, they will remain at an angle of 180 degree with each other. So remaining 180 degree with each other, the overall shape of this molecule will be linear. So carbon dioxide molecule is having shape that is a linear shape, because around carbon within this molecule there are only bond pairs. Now next, moving towards this molecule, BF3 molecule. Boron in its valence shell having 3 electrons around boron. So after that, it will combine with fluorine atoms in this fashion. Fluorine atoms in this fashion. So there are now only 3 bond pairs around boron and not any kind of lone pair. So shape of this molecule will be regular shape. That regular shape is the shape of a triangle. So BF3 is triangular in shape. After that, they are maximum away from each other. That angle is equal to angle in an equilateral triangle, that is equal to 120 degree. I will write the shape of this molecule. Boron is at the center of an equilateral triangle. After that, these 3 atoms are oriented towards the corners of a triangle. Among these bond pairs, there is an angle of 120 degree. So overall shape of this molecule is a triangle. Next, moving towards this ethane molecule. Methane molecule is having carbon as central atom. Around carbon there are 4 electrons. Carbon having 4 valence electrons. They will bond with 4 hydrogen atoms. So there are only bond pairs around carbon within methane. These bond pairs I may draw in this way. These are the bond pairs around carbon in methane, but they are not oriented in space just like a square. But we know the fact of valential electron pair repulsion theory, that is, these bond pairs have to orient in space in such a way such that there will be maximum distance in between them. That maximum distance is possible if I will call this shape as tetrahedral, bond angle being equal to 109 degree 28 minutes. So tetrahedral shape is the best fit shape in space for a molecule having 4 bond pairs around the central atom, and the 4 bond pairs are oriented in space along the 4 corners of a tetrahedron. After that, we will move towards this molecule, PCl5, phosphorus pentachloride. This one, phosphorus having 5 valence electrons in its valence shell. These are the 5 valence electrons. They will combine with chlorine atoms in this way. Chlorine atoms in this way. So there are now 5 pairs of electrons around phosphorus. They will orient in space in such a way such that again there will remain maximum distance in between the bond pairs. They are the only bond pairs around phosphorus. They will remain at an angle of these 3. We call these 3 as equatorial positions. The chlorine atoms at these positions, they are at 120 angle with each other. However, this one is perpendicular to the plane of triangle. This one also perpendicular to the plane of triangle. This perpendicular from below side and this perpendicular from upwards. These perpendicular phosphorus chlorine bonds, they are at an angle of 90 degree with the bonds which are in the plane of triangle. But this shape we call as trigonal bipyramidal. So this is a regular shape. This is the best fit shape. This is the most stable shape for a molecule having 5 bond pairs around the central atom. So any molecule having 5 bond pairs around the central atom, it will have the shape of trigonal bipyramidal. After that, we will move towards this example, SF6. Sulfur is having 6 number of valence electrons in its valence shell. So I have written these are the 6 valence electrons around sulfur within this molecule. So this sulfur atom will combine with 6 fluorine atoms in this fashion. These are the 6 fluorine atoms around sulfur. After that, we will count these numbers. They are in total these 6 pairs, only bond pairs around sulfur. So they will obtain the geometry of an octahedron. Sulfur at the center, these 4, they are at corners of a square. After that, above the plane of square there is 1 bond, below the plane of square there is 1 bond. So this overall geometry is the geometry of an octahedron. So any molecule having 6 pairs, but they are bond pairs. They must be bond pairs. If they are surrounding the central atom within any example, just like as in sulfur hexafluoride, then the shape of that molecule will be octahedral. Similarly, we will move towards this IF7. So there are again 7 pairs, because we know iodine is having 7 valence electrons. There are 7 pairs around this iodine atom. They are oriented in space in such a way such that first of all a pentagon is formed. That is plane of the molecule. This one pentagon formed, one above the plane of pentagon, another one below plane of pentagon. So in this way the overall shape of this molecule is pentagonal bipyramidal. The shape is, again I will repeat, pentagonal bipyramidal. So any molecule having 2 pairs around, but they must be bond pairs. They must be bond pairs. If they are around the central atom of a molecule, then shape of the molecule will be linear. If there are 3 bond pairs around the central atom, then shape of that molecule will be triangular. If 4 bond pairs, then shape of that molecule will be tetrahedral. After that, if there are 5 bond pairs, then shape of that molecule is trigonal bipyramidal. If there are 6 bond pairs around the central atom, then the shape of that molecule is octahedral. If there are 7 pairs, bond pairs around the central atom, then the shape of that molecule is pentagonal bipyramidal. So these shapes we call as regular shapes. Simply, I mean to say, if there are only bond pairs around the central atom within any molecule, then that molecule will have a regular shape. Otherwise, if in addition to bond pairs, there will be now lone pairs. Those lone pairs will distort the geometry from the regular shape. So these examples means those molecules having bond pairs plus lone pairs. These examples we will discuss in the next video. So far you will cover this portion, that only those molecules having bond pairs around themselves, around the central atom, within these molecules, their shapes are regular. These regular shapes are noted here. We will first of all remember these things. After that we will move to those molecules in which around the central atom there are bond pairs plus lone pairs. That will be done in the next video. Thank you.